In the last lecture, I have given several problems of probability. The purpose of these problems was to show the applications of various rules, for example, addition rule, the concept of conditional probability, the theorem of total probability and the Bayes theorem. Today also I will spend some more time on solving problems. Many of these problems are also taken from question papers of some competitive examinations like joint entrance examination and some other examinations. Again you can see that most of these problems will utilize all the concepts that we have discussed till now. Also I would advise that please go through the chapter on permutations and combinations, because some of the probability problems involve the concepts of permutations and combinations. So, it would be better if the students are well prepared for that. So, let me start with some problems. The probabilities of observing a 6 when 3 dice. So, let me name them D1, D2, D3 are tossed independently are 1 by 6, 1 by 5, 1 by 4 respectively. So, that means if the die D1 is tossed, then the probability of observing a 6 is 1 by 6. If the die D2 is tossed, then the probability of observing a 6 is 1 by 5. That means it is a biased die. Similarly, if D3 is tossed, then the probability of observing a 6 is 1 by 4. Again it is a biased die, and the dice are tossed independently. Now, the problem is like this, a die. So, that means out of D1, D2, D3 is chosen randomly. So that the probability of choosing Di is proportional to 1 by I for I is equal to 1, 2, 3. This die is tossed. What is the probability that a 6 is observed? If a 6 is observed, what is the probability that die D2 was chosen? So, let me again repeat the problem. There are 3 dice. If dice D1 is tossed, then the probability of head is 1 by 6. If the die D2 is tossed, then the probability of 6, not 1 by not the head, it is 1 by 5. If the die D3 is tossed, then the probability of 6 is 1 by 4. Now, one die is chosen at random, but the probability of each die is not 1 by 3. The probability is actually proportional to 1 by I. That means, if Di is chosen, the probability will be some alpha by I for I is equal to 1, 2, 3. Then this particular die which has been chosen is tossed, and then some question is asked, that is, what is the probability that a 6 is observed if a 6 is observed, what is the probability that the die D2 was chosen? So, let us look at the solution here. Let E denote the event that a 6 is observed. Okay, a 6 is observed, and let AI be the event that die DI is chosen for I is equal to 1 to 3. So, then if we consider probability of AI, so probability of AI is some alpha by I for I is equal to 1, 2, 3. Now, we are choosing among from these 3 dice only, therefore, the sum of probability of A1 plus probability of A2 plus probability of A3, it will be equal to 1. That means, these events A1, A2, A3 are exhaustive. So, you will have probability of A1 plus probability of A2 plus probability of A3 is equal to 1. So, probability of A1 is alpha by 1, probability of A2 is alpha by 2, and the probability of A3 is alpha by 3. So, that is equal to 1. So, if you simplify this, this is becoming 11 by 6. So, you get alpha is equal to 6 by 11. So, if we substitute back in the probability of AI, I get probability of AI is equal to 6 by 11, sorry, probability of A1, probability of A2 is 3 by 11, and the probability of A3 is equal to 2 by 11. So, now what is the probability of E given A1? That is 1 by 6. The probability of observing a 6 when second coin is chosen is 1 by 5, and the probability of observing a 6 when the third dice is chosen is 1 by 4. Now, by theorem of total probability, probability of E is equal to sigma probability of E given AI into probability of AI, I is equal to 1 to 3. So, all the values are available to us. So, it is becoming probability of E given A1, that is 1 by 6, into probability of A1, that is 6 by 11, probability of E given A2, that is 1 by 5, into probability of A2, that is 3 by 11, plus probability of E given A3, that is 1 by 4, into probability of A3, that is 2 by 11. So, if we add up these terms, we get 21 by 110. So, the probability of observing a 6 is 21 by 110. Obviously, since the at least 2 of the dice were not unbiased, they were not fair dice. Therefore, you can see the probability of a 6 is not 1 by 6, it is 21 by 110. So, now let us look at the second part of it. If a 6 is observed, what is the probability that the die D2 was chosen? That means, we want what is the probability of A2 given that a 6 is observed. So, this is a direct application of Bayes theorem. So, this is equal to probability of E given A2 into probability of A2 divided by probability of E. So, that is equal to 1 by 5 into 3 by 11 divided by 21 by 110. So, this can be easily simplified and you get it as equal to 2 by 7. So, this is an application of by Bayes theorem. So, let us take another problem of a similar nature. So, there are 3 shooters, let us call them S1, S2 and S3. So, they hit a target successfully with respective probabilities 2 by 5, 1 by 3 and 3 by 7. So, the probability that the shooter S1 will hit the target is 2 by 5, the probability that the shooter S2 will hit the target is 1 by 3, the probability that the shooter S3 will hit the target is 3 by 7. So, they shoot simultaneously and independently of each other. What is the conditional probability that S2 missed the target given that there were exactly 2 hits? So, let us define the events. We define event Bi that Si hits the target for I is equal to 1, 2, 3. Then the events B1, B2, B3 are independent, because it is given that the shooters shoot independently of each other. B1, B2, B3 are independent. Also, we are given what is the probability of B1, what is the probability of B2, what is the probability of B3, that is 2 by 5, 1 by 3 and 3 by 7. We can write it here. Then probability of B1 is equal to 2 by 5, probability of B2 is 1 by 3 and probability of B3 is equal to 3 by 7. So, let us consider A to be the event that there are 2 hits. Then what is the event A? Then the event A is okay. We have to express it in terms of B1, B2 and B3. So, if there are 2 hits, that means we can have the situation that B1 and B2 hit and B3 does not hit. Similarly, we can have the first and third hit, second does not hit, or second and third hit and the first does not hit. So, we can say A is B1 intersection B2 intersection B3 complement. So, it means the shooter 1 and 2 they hit and the third one misses. So, I have written B3 complement union. We can have B1 and B2 complement and B3. So, it means the first and the third shooter are successful, whereas the second shooter is unsuccessful. Union B1 complement intersection B2 intersection B3. It means that the second shooter and the third shooter, they are successful, whereas the first shooter is not successful. So, what we have done? We have represented the event A as a union of, so this is one event, this is one event and this is one event. These three are disjoint events. Why they are disjoint? Because in this one, for example, B3 complement is there and here B3 is there. So, certainly this one is a subset of B3, this one is a subset of B3 complement, because these are intersections of the events. So, these two cannot have any element in common. Similarly, if I take second and the third one, here B1 complement is there, here B1 is there and here B1 complement is there. So, again they are disjoint. Similarly, if I look at the first and the third, so here B3 complement is there, here B3 is there. So, they will be independent. So, if I consider probability of A, then I will get it is equal to probability of B1 intersection B2 intersection B3 complement plus probability of B1 intersection B2 complement intersection B3 plus probability of B1 complement intersection B2 intersection B3. Again, in one of the earlier problems I have shown that if two events are independent, then their complementations are one complement or the other, they are all independent. So, if B1, B2, B3 are independent, I will have B1, B2 and B3 complement independent, B1, B2 complement and B3 independent, and B1 complement B2 and B3 independent. So, the probabilities of these intersections become product of the probabilities. So, for example, the first one becomes probability of B1 into probability of B2 into probability of B3 complement. Similarly, if I look at the next one, then it is probability of B1 into probability of B2 complement into probability of B3 plus probability of B1 complement into probability of B2 into probability of B3. Now, all the values of these probabilities of B1, B2 and B3 are available. So, we can substitute them here. Probability of B3 is 3 by 7. So, probability of B3 complement will become 4 by 7. So, this term can be easily simplified and we get it to be equal to 29 by 105. So, the probability that there are exactly 2 hits is equal to 29 by 105. Now, if I look at the question that is asked here, what is the conditional probability that S2 missed the target, given that there were exactly 2 hits. So, if I say S2 missed the target, so B2 is the event that S2 hits the target. So, B2 complement. So, we have to then calculate the probability of the required probability is equal to probability of B2 complement given A, that is equal to probability of B2 complement intersection A divided by probability of A. Now, what is B2 complement intersection A? So, if I look at the event A, so if I put B2 complement intersection A, then it will become B2 complement intersection with the first term union B2 complement intersection with the second one union B2 complement intersection with the third one. Now, you can notice here that in the first term it is B2. So, if I take intersection with B2 complement, I will get 5. In the third one also it is B2. So, if I take intersection with B2 complement, I will get phi. So, I will get only the term B1 intersection B2 complement intersection B3 here. So, this event is equal to probability of B2 complement intersection B1 intersection B3 divided by probability of A. So, the term that we have already simplified divided by probability of A. So, this term is equal to 2 by 5 into 2 by 3 into 3 by 7 divided by 29 by 105. So, this value turns out to be this is equal to 12 divided by 29, because this 105 and 105 will get cancelled out and here we will get 12 by 29. So, the conditional probability of the event that the shooter S2 missed the target, given that the exactly two shooters were able to shoot, that is equal to 12 by 29. So, here this is an example of conditional probability, as well as here I have used the concept of union of disjoint events and the concept of independence of events. So, one extra thing that has been used, you please note here, that if any set of events are independent, then if I include complementations of some of the events, then they are also independent. As I have mentioned in the beginning, B1, B2, B3 are independent, but here I am using independence of B1, B2 and B3 complement, independence of B1, B2 complement and B3, and B1 complement, B2 and B3. So, you note here that although these things look extremely simple because we are able to use the set theoretic notation, but there are in each problem several concepts that are being applied simultaneously. Let me give another example of the conditional probability. So, a computer producing factory has only two plants, say T1 and T2. Plant T1 produces 20% and plant T2 produces 80% of the total computers produced. Uh, 7% of the computers produced by the factory turn out to be defective. Further, it is known that probability that computer is defective given that it is produced in plant T1 is 10 times the probability that the computer is defective given that it is produced in plant T2. Now, a computer produced in the factory is randomly selected and it is not defective. What is the probability that it is produced in plant T2? So, the language is long. So, let me read out the problem once again. So, there is a factory which produces computers and the factory has two plants. So, they are named as T1, T2. The total products 20% is produced by plant T1 and remaining 80% is produced by plant T2. Also, it is found that 7% of the product is defective. And additional information that is also given, that the computers produced by plant T1 have 10 times the probability of defective as it compared to that it is produced in plant T2. So, now if a computer is produced in the factory is randomly selected and it is found to be not defective, then what is the probability that it is produced in T2? So, let us define the events now. Let A be the event that the computer is defective, and I use the notation Bi that it is produced in plant Ti for I is equal to 1, 2. Then it is given that probability of B1 is 1 by 5 and probability of B2 is equal to 4 by 5. Because it is given that plant T1 produces 20%. So, that is 1 by 5 and plant T2 produces 80%. So, probability of B2 is 4 by 5. So, it is also given that the probability of defective is 7 by 100. So, if we apply the formula, probability of A, that is equal to probability of A given B1 into probability of B1 plus probability of A given B2 into probability of B2, that is by theorem of total probability. You can note here that the condition for the theorem of total probability are satisfied here, because you have two mutually exclusive and exhaustive events B1 and B2, and then there is an additional event A, and the probabilities of A given B1, A given B2, etc. can be used here. Now, you are given that this condition, probability that the computer is defective. Now, this is A given B1 is 10 times probability of A given B2. So, let us make some notation here. Let us take, say, probability of A given B2 is equal to, say, alpha. Then probability of A given B1, it will become 10 alpha from this condition. Probability of A given B1 is equal to 10 times probability of A given B2. So, if I choose probability of A given B2 to be alpha, then probability of A given becomes 10 alpha. So, now let me call it 1. So, in equation number 1, let us substitute this. Left hand side is probability of A, that is 7 by 100, is equal to probability of A given B1, that is 10 alpha, into probability of B1, that is 1 by 5, plus probability of A given B2, that is alpha, into probability of B2, that is 4 by 5. So, that is equal to 14 alpha by 5. So, we can easily simplify this, that will give me alpha is equal to 1 by 40. So, I have actually evaluated probability of A given B2 as 1 by 40 and probability of A given B1 as 1 by 4. Probability of A given B2, it becomes 1 by 40 and probability of A given B1 becomes 1 by 4, that is 10 times this. Okay. So, now what is the question that is asked? What is the probability that it is produced in T2 given that it is not defective? That means, in terms of events, if I write, the required probability is probability of B2, it is produced in plant T2 given that it is not defective, that is B2 given A complement. So, here I can apply again the conditional probability. So, that is probability of B2 intersection A complement divided by probability of A complement, and this is nothing but probability of A complement given B2 into probability of B2 divided by probability of A complement. You can say it is Bayes theorem or it is multiplication rule. So, probability of A complement given B2, that you can calculate from here, because probability of A given B2 is there. So, this is becoming 1 minus 1 by 40 into probability of B2, that is 4 by 5 divided by probability of A complement. So, probability of A is 7 by 100. So, this is nothing but 93 by 100. So, this term we can easily simplify and we get 78 by 93. So, one thing that you can observe here, that the probability of B1 is actually 1 by 5 and the probability of B2 is 4 by 5. But if I am looking at the event that it is not defective, then the probability of B2 is 78 by 93. So, that has become more than 3 by 4. The reason is that the number of defective items from the second plant is much less. So, therefore, this probability has become more. In this problem, you can notice I have used several concepts. One is that concept of total probability. Then we have used the theorem of total probability to solve a certain equation which gives me the original conditional probabilities. Then I have applied the concept of conditional probability, or you can say Bayes theorem, to evaluate the final probabilities. Let me now give one example of enumerative probability. That means, we have to count the number of cases. So, suppose there are there are let me call them again T1 and T2, and they play two games against each other. Okay. Then probability that T1 wins a game, that is 1 by 2. Probability the game is draw, is 1 by 6 and the probability that T2 wins the game, wins a game, is say 1 by 3. Okay, so they are playing against each other. So this event T1 wins is also equivalent to saying T2 loses, and if the game is draw means both are not winning, or you can say both are not losing. Similarly, T2 wins a game means T1 actually loses the game because they are actually playing against each other. The winning team gets 3 points, the losing team 0 points, and for a draw both teams get 1 point each. So let us use some notation. Let x be the total points by team T1 and y be the total points by team T2 after 2 games. Then find, say, what is the probability of x is equal to y, what is the probability of x greater than y, what is the probability x less than y. As I mentioned, this is a case of enumerative probability. We have to actually count the cases in which we get these events. So, for example, if I say x is equal to y, since there are 2 games, in what way x and y will be same? That means the total points by team T1 and total points by T2 are same. So, that is possible if both games are drawn, or the first game, or you can say one game is won by say T1 and another game is won by T2. So, we can say T1 wins one game and T2 wins one game. So, in this case also both will get 3 points. In the first case, if both the games are drawn, both the teams get 2 points. So, here x and y both are 2 and here x and y both are 3. So, these are the case when x is equal to y. Again you can see I have used the mutually exclusive and exhaustive events here. The event that both the games are drawn, or the event that T1 wins one game and T2 wins one game, these two are mutually exclusive and exhaustive. Therefore, the probability of the union is equal to the sum of the probabilities. Now, in order to evaluate that both the games are drawn, we have to actually look at the probability of one game being drawn and the second game being drawn. Now, this can be calculated only if I make the assumption that the games are played independently. So, we have to write that assumption that the games are played independently. So, in that case, let us calculate this probability. Both the games are drawn. So, the probability of a draw is one by 6. So, it becomes 1 by 6 and in the second game also the same outcome. So, 1 by 6. So, here I have made use of the independence. In the second case T1 wins one game. So, the probability is half, and T2 wins one game, the probability is 1 by 3. But here you can choose the order in which the games are played. For example, the first game may be won by T1 and the second may be by T2, or the reverse. So, there are two such cases. So, I have to multiply by 2. So, this we can easily evaluate, it is equal to 13 by 36. Similarly, let us look at what is the probability of x greater than y. So, x greater than y means T1 wins both games, or T1 wins one game and one game is drawn. Now, there is no other possibility, because if T2 wins, then his points will become equal to T1 or it will become more. So, let us look at, if T1 wins both the games, his probability of winning is 1 by 2 into 1 by 2. He wins one game, probability is half, and drawing is 1 by 6. But again here you can choose the order in which T1 will win and the game is drawn. So, there are two such possibilities. So, if you add these two, you get 5 by 12. You can say it is 15 by 36. So, if you calculate what is the probability of x less than y, then that is equal to 1 minus probability of x is equal to y and probability of x greater than y, that is equal to 2 by 9. That is, you can say 8 by 36. So, we have calculated the probabilities of all options. In this problem, I have made use of the concept of independence, the concept of mutually exclusive and exhaustive events. Let us look at another problem in which again I have to count the number of cases. So, box 1. So, this is again a problem which is from one of the joint entrance examination question papers. If you see the old question papers, this problem is there. I will show you how the solution is described. So, box 1 contains 3 cards bearing numbers 1, 2, 3. Box 2 contains 5 cards bearing numbers 1, 2, 3, 4, 5, and box 3 contains 7 cards bearing numbers 1, 2, 3, 4, 5, 6 and 7. A card is drawn at random from each of the boxes. Let xi denote the number of the card drawn from the ith box for I is equal to 1, 2, 3. Find the probability that x1 plus x2 plus x3 is odd. Find the probability that x1, x2, x3 are in an arithmetic progression, which we use the term AP. Okay, so in box 1 there are 3 cards, in box 2 there are 5 cards, and in box 3 there are 7 cards. So, from each box when we are choosing the card, then from box 1 there are 3 possible ways, from the box 2 there are 5 possible ways, and from box 3 there are 7 possible ways. So, the total number of ways of choosing or drawing the cards x1, x2, x3, that is 3 into 5 into 7, that is equal to 105. So, now in part 1 we have to look at the number of cases in which x1 plus x2 plus x3 is odd. So, now see, one thing is that we start writing down from 1 you can have 1, then second you have 1, then from the third one you have 1. So, like that you can start counting, but it will take long time. So, let us develop a systematic number theoretic approach. So, we can say, for example, in x1 you have only 3 possibilities. So, I can have x1 as x1 can take 3 values. So, if x1 is equal to 1 or 3, and then you want x2 plus x3, that should be even, because if x1 is odd, then if you add an even number, then you will get an odd number. So, then x2 plus x3 must be even. Similarly, if x1 is equal to 2, then x2 plus x3 must be odd. So, let us look at this, is much easy to look at. So, either x2 and x3 are even. So, that is possible in how many ways? For x2 you have even possibilities 2 and 4, and for x3 you have even possibilities 2, 4 and 6. So, there are total 2 into 3, that is 6 cases. Or you can have x2 and x3 both are odd, because sum of 2 odds is even. So, now how many possibilities? For x2 odd you have 1, 3, 5, that is 3 possibilities, and for x3 1, 3, 5 and 7, that is 4 possibilities. So, that are total 3 into 4, that is 12 cases. So, total cases is equal to 6 plus 12, that is equal to 18, and then x1 can take 2 values. So, this will become 2 into this. So, that is 2 into 18, that is equal to 36 cases. That means, if x1 is equal to 1, 3, then total number of cases is 36. Now, second part can be, if x1 is equal to 2, then x2 plus x3 must be odd. Now, for odd, how many cases will be there? So, that is, so x2 you can have odd and x3 even, because sum of odd plus even is odd. Now, x2 odd you can have 1, 3, 5. So, there are 3 cases, x3 even there are 2, 4, 6, 3 cases. So, total 9 cases. Similarly, you can have x2 even and x3 odd. So, x2 even there are 2, 4, that is 2 cases, and x3 odd there are 1, 3, 5 and 7, 4 cases. So, there are total 8 cases. So, in this case you are getting total number of cases is equal to, so in this case total number of cases is equal to 9 plus 8, that is equal to 17. So, total number of cases in which x1 plus x2 plus x3 is odd is equal to 36 plus 17 that is equal to 53. So, the probability is 53 divided by 105. Let us look at the second case. What is the probability that x1, x2, x3 are in an arithmetic progression? So, for arithmetic progression you have to see that x1, x2, x3 are chosen in such a way that x1 minus x2 and x2 minus x3 they are same, that is the common difference is there. Now, what are the possibilities of the common differences? So, let D be the common difference. Let us see what are the ways in which this can be done. So, for example, if I choose x1 is equal to 1, then x2 and x3 can be 1 1 each. So, that is 0 common difference, or you can have 1 2 3. So, that is 1 common difference. You can have 2 2 2 2 3, but then 4 is not possible. Then you can have 3, but then 3 3 3 is possible, 3 4 and so on is not possible. You can have 3 2 1, that is the minus 1 as the difference, or you can have 1 3 5, that is possible, or you can have 2 4 6, or you can have 3 5 7. So, let us look at all these combinations. So, D can take values minus 1, 0, 1, 2 and 3. Then what are the number of cases? I told you for minus 1 the only possibility is that x1 should be 3, x2 should be 2 and x3 should be 1. So, the total number of cases is only 1. What are the possibility for 0? So, 0 is possible when x1, x2, x3 are equal, that means you can have 1 1 1, 2 2 2 or 3 3 3. So, there are 3 such cases. Common difference 1, that is possible if you have 1 2 3, 2 3 4 and 3 4 5. So, there are total number of 3 cases. Again let us look at the common difference 2. So, common difference 2 can be possible if you have x1, x2, x3 as 1 3 5, 2 4 6 or 3 5 7. So, total number of cases is 3. Then the common difference 3 is possible if I have 1 4 7. So, there is only one possibility because 2 5 and then 8 is not there. So, this is the total number of cases. Total number of cases is 11. So, the required probability that that x1 plus x2 plus x3 that is x1, x2, x3 are in an arithmetic progression is 11 by 105. Such kind of problems are usually asked in the competitive exams. I will spend some more time on solving JEE type of questions in the next class, and I will spend few lectures on the discrete distributions. So, please follow the next few lectures also, because I will be solving many interesting problems which are asked commonly in the entrance examinations. Thank you.